Hello everyone. Today we are going to talk about lightweight cryptography and Internet of Things. Myself Rukmini Goli and my teammates are Pradeep Parvataneni and Prithvi Vahan Raj Ankus. So let's see the contents we have covered. First is what is IoT and the threats associated to the IoT and why the lightweight cryptography is important. And also the papers we have reviewed and the conclusion we have come upon. And we have also added few of the references for the papers which we have reviewed. So let's see what is IoT. Internet of Things or IoT is influencing our lifestyle from the way we react to the way we behave. From air conditioners that you can control with your smartphones to smart cars providing the shortest route or your smart watch which is tracking your daily activities. Everything is on IoT. IoT is a giant network with connected devices. These devices gather and share data about how they are used and the environment in which they are operated. It's all done using sensors. Sensors are embedded in every physical device. It can be your mobile phone, electrical appliances, barcode sensors, traffic lights, and almost everything that you can come across in your day-to-day life. These sensors continuously emit data about the working state of the device. But the important question is, how do they share this huge amount of data and how do we put this data to our benefit? Here, IoT provides a common platform for all these devices to dump their data and a common language for all these devices to communicate with each other. Data is emitted from various sensors and sent to IoT platform security. IoT platform integrates this collected data from various sources. Further analytics is performed on the data and valuable information is extracted as per requirement. Finally, the result is shared with other devices for better user experience, automation, and improving efficiencies. So let's see the architecture of IoT. The IoT architecture has 4 layers to it, which is sensing layer, network layer, data processing layer, and the application layer. Sensing layer, also known as the device layer. The examples would be sensors, thermometers, pressure sensors, which draw the data and send to embedded device. Next comes the connectivity layer, which can be Wi-Fi, Bluetooth, etc. Followed by the third layer, that is data processing layer. This is the layer where all the analysis is done on the data collected and decisions are made. User interface or the application layer is the last layer which we users mainly use and interact. On a new computing environment called Internet of Things or Smart Object Networks, a lot of constrained devices are connected to the internet. The devices interact with each other through the network and provide new experience to us. In order to enjoy this new environment, security of constrained end nodes is very important. If one of the nodes were compromised, the network might be suffered seriously. However, it is not easy to implement sufficient cryptographic functions on constrained devices due to the limitation of their resource. So as we previously discussed, there are several ways on IoT network can be compromised. We can classify them to physical attack, side channel attacks, cryptanalysis attacks, and software attacks and network attacks. As the number of applications of IoT increases, the amount of raw data that is generated also increases. And also the attacks that impact the security and privacy of these applications will definitely increase. Since IoT has made its way to very important sectors like healthcare and financial, defense against the threats is very important. So, coming to the important question, what is lightweight cryptography and why lightweight cryptography? Lightweight cryptography is a cryptographic algorithm or protocol tailored for implementation in constrained environments like sensor networks or healthcare IoT or radio frequency identifications, etc. Lightweight cryptography contributes to the security of smart object networks and are more practical to use. Cryptographic technologies are advancing and new techniques on attack, design, implementations are extensively studied. Lightweight cryptography is one of the state-of-the-art technology in the field of cryptography. So coming to the question, why lightweight? Efficiency of end-to-end communication. In order to achieve end-to-end security, end nodes have an implementation of a symmetric key algorithm. For the low resource devices, example, battery powered devices, the cryptographic operations with the limited amount of energy consumption is important. Application of lightweight symmetric key algorithm allows lower energy consumption for end devices. And also, applicability to lower resource devices, the footprint of the lightweight cryptography primitive is smaller than the conventional cryptographic ones. The lightweight cryptographic primitives would open possibilities for more network connections with lower resource devices. So, let's see what's the present development in lightweight cryptography. Few of the lightweight block ciphers are DESL, Present, Clefia, Simon, Spec, and T. And here are the factors which would differentiate them with non-lightweight cryptography. Let's consider an example. Let's block size. So the lightweight cryptography would vary between 32 bits, but the non-lightweight cryptography would have 64 to 128 bits. The same goes with the key size and the rounds. Since the advanced cryptographic standard is selected, many block ciphers with lightweight properties have been proposed. Among them, Clefia and Present are well studied about their security and implementation are ready to use in practical systems. Apart from this, NIST's new cryptographic algorithm SHA-3 has attracted a lot of attention. In this slide, we can see the lightweight cryptography versus the conventional cryptography. One of the papers we studied have done a comparison between the lightweight cryptography and conventional cryptography focusing on hardware properties. In this graph, higher slope indicates higher efficiency, which leads to lower energy consumption. This compares lightweight cryptography block ciphers, Clefia, with conventional block ciphers, AES, Camellia, and Seed. We can see that Cephala has advantage in hardware gate efficiency over other ciphers. Coming to this slide, we will be discussing an ultra-lightweight block cipher, Present, which is developed by Orange Labs in Ruhr University and Technical University of Denmark. Present has a compact size of 2.5 times smaller than AES. You can clearly see the difference between a lightweight cryptography and a non-lightweight cryptography cipher. And the block size is 64 bits and the key size is 80 to 128 bit. This has a lower power consumption and gives a high chip efficiency. And the structure used is an SPN. SPN is a substitution permutation network. So from here on, my teammate Prithvi would take over and explain you guys the second part of our presentation. Thank you so much.
Thank you, Rukmini. I'm Prithvi. I will be taking over the second part of this presentation. For this project, we have reviewed several papers, and one of those is Intelligent Security Framework for IoT Devices. This paper majorly discusses about Internet of Things network and the issues related to the security of it. This paper also proposes a secure IoT framework to ensure an end-to-end security from an IoT application to IoT devices. And the proposal system implements dual mutual authentication First, lightweight asymmetric key cryptography is used to provide authentication between sensor node and device gateway. The sensor node's unique ID and device gateway's unique ID is used to create a secret key digital certificate using AES algorithm. Second, the device gateway and the cloud service is mutually authenticated using public key encryption digital signature. Before we jump right into what this paper discusses, let's go through some of the existing works in the field of IoT. The IoT broker registration protocol, in which the device registration and authentication process is discussed. Routing protocol and its security features, where various routing protocols are classified, including the threats related to them. An end-to-end security-based protocol where using IoT device, IoT broker, and IoT application, a secure environment is proposed. Data management and deduplication in cloud computing, it relates to deduplication of the encrypted data while supporting a secure data access control. VM replication based protocol, where the use of VM replication to improve the survivability of mission critical applications in cloud systems is proposed, and some surveys related to machine and third-party based communications. The intelligent security framework proposed in this paper has some prerequisites, which are master key repository maintaining the details of unique ID of IoT nodes, device gateways, IoT service gateway, and cloud services, and it generates the key pair using learning with errors encryption. IoT node communicates the master key repository by offline-online mode and acquires master key repository's public key. IoT nodes encrypts its unique ID and the timestamp with its private key and double encrypts with master key repository's public key and sends it to the master key repository. Device gateway encrypts its unique ID and the timestamp with its private key and double encrypts with master key repository's public key and sends to master key repository. The node encrypts the message and timestamp using service device session key. The device gateway then encrypts the message and timestamp using secret service session key. The node sends the message, secret device session key, and double encrypts it using its private key and device gateway's public key. A mutual and double authentication schemes have been proposed, which reduces the traffic by eliminating the fault and fake packets. This system also provides security against quantum attacks, improves the performance, and reduces the bandwidth consumption. As IoT is coming out as an emerging technology from the last few decades, and the demand for the devices based on IoT are also increasing. Therefore, the dependency on this technology is increasing in parallel. This calls for a proper encryption method which is cost-effective, reliable, size-effective, and also uses a small key size. Many of the encryption methods are proposed till now for the same, but still we have a room for improvement. The effect of IoT on the internet and economy are increasing, with somewhere in the range of 100 billion devices associated with IoT and a worldwide financial effect of nearly 11 trillion by 2025. In one of the papers which we have studied, the methodology used for developing the algorithm for lightweight encryption algorithm is stated. It consists of some of the steps which need to be followed. While doing the development for the security algorithm for IoT-based devices, we need to take care some of the constraints like memory space used, cost effectiveness, size of key, number of gates used, and measure of efficiency. The steps include key expansion, followed by the key management protocol, then the encryption, after which the decryption of the codes finally is followed by an evaluation of the performance. This flowchart describes the steps involved in developing such an algorithm. Key expansion. Key expansion is the main process for generating unique keys for encryption and decryption. Key management protocol. The key can be securely sent to the encoder via leap, which is again a lightweight algorithm used for cryptography in IoT-based devices. It is very simple and energy-saving protocol that is designed for some large-scale wireless sensor networks. And then encryption protocol. The encryption process is usually known as coding in easy language, and the process of encryption starts as soon as the key is generated by key expansion block. It is safely sent through and is received by the encoder. The secure communication channels are performed by the leaf protocol. Decryption is a process of taking the encoded or the encrypted text and converting it back to readable text which computer can read and understand. This describes a method to decrypt the data manually or via using the proper codes or keys. For performance analysis, various cryptographic algorithms are used and an image is processed. Later, the results are compared and analyzed in the paper. These are some of the characteristics lightweight cryptography offers: smaller block sizes, smaller key size, simple round logic based on simple computations, simple key scheduling. These characteristics resolve some issues like physical area, memory, battery power, computing power, etc. Also, strong structures like SPN or FNS will help in resolving the issues like minimum security strength, attack models, side channel attacks. Although there were several researches done in the past decade and are ongoing, there are some research challenges in lightweight cryptography. The ideal algorithm needs to maintain a proper balance among cost, performance, and security. Any two of these three design goals, security and low costs, security and performance, low cost and performance, can be easily optimized, whereas it is very difficult to optimize all three design goals at the same time. My teammate Pradeep will be taking over from here to discuss the third part of this presentation.
Hi everyone, this is Pradeep. I'll be focusing on the review of another paper and will answer the questions that are specified in the beginning of our literature review. The name of the paper is Security for Automation in Internet of Things Using One-Time Password. This paper focused on a lightweight authentication mechanism for IoT devices and users. Some of the principles in lightweight identity-based elliptic curve cryptography plan and Lamport's OTP calculation are used in this paper. Coming to OTP, OTP stands for one-time password. It is a combination of numeric and alphanumeric characters. This is used by the client for validating his session. This OTP cannot be used for multiple login sessions. It is valid only for one session. It is more secure than a password because of two reasons. The first reason is it is not static. That is, it will be varying for each session. So it is not vulnerable to replay attacks. The second is if the password is known to attackers, they can use it to log in as a user any number of times. But an OTP is valid for only one session. Even though if they know it, it will not be of any use to the attackers. Before sending the OTP to the client, the OTP will be encrypted and it is decrypted after receiving from the client and is compared to authenticate the user. There are two kinds of authentication, one-way authentication and two-way authentication. This paper uses two-way authentication. So the main difference between one-way authentication and two-way authentication is that in one-way authentication, only the server is validated by the client, but in two-way authentication, both the client and server authenticate with each other. This paper considered the design for a home automation project. There are two parts in this architecture. One is the hardware design and the other is OTP generation and encryption. In the hardware design, a Raspberry Pi with 512 MB RAM is used. So it is a Raspberry Pi 3 model which has an inbuilt Wi-Fi. It has several sensors for converting the physical quantity to electrical signal. It has a MCP43204 for converting the analog signal to digital, and this digital signal is fed into the Raspberry Pi. It has a PIR sensor for person detection and a relay for light and fan control. They use the Python programming language. They specified that they have chosen Python because it is easy to use, simple to learn, and also most suitable for certifiable applications. In the second part, OTP generation and encryption, they used ECC for OTP generation. This OTP is encrypted with the AES encryption algorithm. A copy of this is stored in MySQLDB, and another copy is sent to the user who requested access to the system. The system decides whether access should be given or not to this requested user based on the secret ID and OTP he provides. It matches the OTP provided by the user with the OTP in the MySQLDB. Are there any improvements that can be made to this existing algorithm? Below are some of the improvements that can be made to this algorithm based on our evaluation. This paper specified that a copy of OTP will be stored in the MySQL Server DB. So what if the database is compromised? They did not specify whether any additional level of security is provided to the database and whether the encrypted or plain OTP is being stored in the database. Some additional research can be done or information can be provided in this area on how they can provide additional security in the database level. Another one is there might be an impact on the performance by storing the OTP in relational database when using with IoT devices. As IoT applications are mostly real-time and critical, so there might be a large number of users who try to authenticate the system or attack the system, which might slow down the process. This paper specified that OTP is a combination of numeric or alphanumeric characters, but it did not mention on how much length the OTP will be on an average and whether the length of OTP will impact the performance or security of the applications or not. The paper can specify the trade-off between length and performance and length and security. Tests can be conducted by generating various length of OTPs. The time taken for encrypting and decrypting them can be measured, which helps us to find the appropriate length for the OTP for balancing between the security and performance. So, the OTP should not be too large or too small. The OTP should also be easy to use. It might be difficult for the users if it is too lengthy or if it uses some characters that might be hard to find on the keyboard, considering old age people. But if it is too small, it might not be that secure. So the OTP should also be balanced between usability and security. The paper can perform some research in this area. The OTP is encrypted using the AES algorithm after its generation. And AES demands high computing resources and consumes more memory, so it might impact the performance. And the paper did not provide any reason or information on why AES is chosen. They can choose some other existing lightweight encryption algorithm for the encryption and decryption process, which might improve the performance. We have focused on several other papers too in the report, but cannot specify them in the presentation due to the time limit. I'll be discussing about the answers to the questions that are specified during the beginning of the literature review. The first question is, what kind of attacks most of the lightweight cryptographic algorithms focus on? If most of them are focusing on handling only a specific set of attacks, what is the reason for that? From the papers we reviewed, most of them focused on preventing DDoS attack. DDoS stands for Distributed Denial of Service. In this attack, multiple attackers send a large number of requests to the device and makes it temporarily unavailable. which affects the valid users for whom the request should be served. The reason for focusing more on these attacks might be because IoT devices are resource constrained, they have less processing power, so they might not be able to handle high load. This can be an advantage to the attackers to impact the performance of the system or make it unavailable by sending a large number of requests to it. And it is an easy way to target these devices. So as there is more chance of this attack, more researchers might have been focused on preventing this attack. This chart shows the type of attack and the number of papers that focused on those attacks. DDoS is focused in 5 papers, followed by side channel and Trojan attack in 2 papers, and the others in 1 paper. This chart shows the year and the number of attacks that are studied or focused on this year. We can see that one number of attacks are focused in the years from 2016 to 2020, and less number of attacks are focused in the years of 2010, 2013 and 2015, with not any focus in the years of 2011 and 2012. The second question is, are there any lightweight cryptographic algorithms that are studied more than others? If so, is there any specific reason for that? Based on our study from the papers, some of the most studied lightweight cryptographic algorithms we found are present, height, Simon, spec, rectangle and HECC. HECC stands for hyperelliptic curve cryptography. The reason these algorithms are studied more is because of their efficient hardware and software implementations and efficient key generation. This chart shows the algorithm and the number of papers that studied them. The most studied algorithms are present, Slafia and ECC. They are studied in 3 papers each, followed by Simon, height, hummingbird, blowfish and rectangle, which are studied in 2 papers each, and the remaining are studied in 1 paper each. The next question is, are there any common things that can be found in the several lightweight encryption algorithms used? The common thing that is found in several algorithms from the papers we reviewed is some kind of key generation. There is one paper which we studied that used mutual authentication for enhancing security, and there is another paper which we studied that focused on preventing DDoS attacks based on the packet's content and IP address. These both can be combined to make the service more resistant against DDoS attacks. There is another work which we studied that used ECC for the OTP generation, which I discussed previously. And there is another work we studied that used HECC for key generation, and they specified that HECC is more efficient than ECC. So this work can use HECC instead of ECC for key generation to achieve better performance. The next question is, has the interest in lightweight cryptography algorithms evolved in the years? Yes, it started around in 2006. The years in which most of the study is done are in 2011, 2013, 2014, 2015, 2016, 2017 and 2020. And there is more study, a bit of more study has been happened in the years from 2014 to 2017. Below are some of the algorithms and the years on which they are most studied from our study. Present was studied in the years of 2007 and 2015. Simon was studied in the years of 2014 and 2017. Preventing of DDoS attacks were studied in the years of 2015 and 2017. Blowfish, rectangle and prince were studied in the year of 2014. Height and hummingbird were studied in the year of 2015. Clean, twine and spec were studied in the year of 2017. HECC with JKP was studied in the year of 2020. ZKP stands for Zero Knowledge Proof, and ECC with OTP was studied in the year of 2017. This chart shows the number of algorithms that are studied per year. We can see that more algorithms are studied in the year of 2017, around 8, followed by 2015 and 2019, which are around 7 in number. These are our references. Our references continued. And thank you everyone for listening to our presentation.